Alright, so let's remind ourselves what we were talking about. Think clear back on Monday and on Friday. Alright, so we started talking about matrix representations a little bit, and we're going to sort of dive deeper into that topic. Now, before we start talking about that, we have to sort of make sure that we understand how to obtain an isomorphism from any vector space, finite dimensional vector space, to a Euclidean space. Alright, so to that end, let's go ahead and take a basis. We'll call this basis B. Okay, so we're going to give this basis a name. It's called B. It's going to have n elements, V1, V2, all the way up until we get to V sub n. This is a basis for a vector space V, we'll say. Be a basis for V. Okay, so one thing to note is that B has n elements, and so I know V has a dimension of n, right? Now it turns out what we can do is define a map. In particular, it's going to be a linear map. So define a linear map. We'll call this linear map T. That takes an element from V and it produces a vector in Rn. Okay? And the way this map is defined is as follows. So I take a little vector, little v, living in capital V, and I send it to the coordinate vector with respect to this fixed basis that I sort of started with. All right. Now it turns out that T is an isomorphism. Yeah, and we showed this in class. I believe it was on Friday, maybe. All right. So T is an isomorphism. So in this sense, any vector space that has a dimension of n is going to be isomorphic to Rn. All right. Okay. So we have to understand that in order to sort of get started with this new topic of matrix representations. All right, so that's what we're going to talk about today. The matrix representation of a linear map. The matrix representation, which I'll abbreviate, of a linear map. All right. Okay, so let's go ahead and get started here. Okay, so we're going to learn by example. We're just going to jump right in here. So let's do the following. Okay, so I'm going to suppose that I have two vector spaces. We'll call them V and W. And V is going to be the vector space, we'll say, of polynomials of degree no more than 3. So V is going to be P3R. And why don't we take W to be, I don't know, P2R, something like that. Okay, so I have two vector spaces. One thing to note is that P3 is, of course, going to be isomorphic to R4, and P2 is going to be isomorphic to R3, right? That's exactly what we just talked about in the review. Because P3 is 4-dimensional, P2 is 3-dimensional, and so I get isomorphisms to R4 and R3. But I get the isomorphisms after I've chosen bases for V and W. All right. So to that end, what I'm going to do is fix bases for V and W. All right. So let's go ahead and let B sub V be the standard basis for P3. So the standard basis for P3, of course, is 1 x squared x cubed. Yeah. And then my basis for W is going to, once again, I'm going to choose the standard basis for W. Is going to be 1x and x squared. Nice. Okay. So after I've chosen my bases, I know I get isomorphisms to R4 and R3 respectively. All right. Now, we're going to talk about the matrix representation of a linear map. So I need a linear map to take the matrix representation of. All right. So what I'm going to do is give you a linear map. So define a linear map. And we're not going to have to prove that this is a linear map. You just have to trust me. 1 second here. So yeah, so let's define a linear map. Okay, so this is a mapping from V to W. by setting, okay, so T of an input vector. Now, an input has the form a plus bx plus cx squared plus dx cubed, because I know the domain here consists of polynomials of degree no more than 3. Okay. And the output is going to be a polynomial of degree no more than 2. And the output vector I'm going to specify is going to be a plus d. That's my constant term. My linear term is just going to be b times x. Then my quadratic term, why not put a plus, I don't know, 2c, something like that. Whoops, and not cubed. I need a squared here. Okay. So now I do in fact have a mapping, and it's a linear mapping that takes me from the space of degree 3 polynomials to the space of degree 2 polynomials. Okay. So my goal is to construct what is called the matrix representation of this map. Okay. So to that end, I could sort of make a somewhat of a definition here. Okay, so a matrix, so this is sort of an aside here. So actually, let's do this in, so this is sort of like an aside, I guess we can say. So a matrix A is a matrix representation of this linear map. Now, in general, matrix representations are going to depend on choices of bases, right? That's why at the very beginning, I specified bases for my domain and my codomain, right? So here in parentheses, you know, we should emphasize that this is with respect to my choice of bases. So with respect to, we said b sub v and b sub w. Yeah, because in general, any matrix representation depends on a choice of bases. Okay. So a matrix A is a matrix representation of T if the following diagram commutes. Now we saw this a little bit on Monday, and I'll sort of explain again what I mean by commutativity of this diagram. So if the diagram commutes. Okay, so what I'm going to do is draw a nice little diagram here. I know I have a mapping that takes me from V to W, right? That is this correspondence that I defined right here. T of a plus bx plus cx squared plus dx cubed is a plus d plus bx plus a plus 2cx squared, right? This correspondence is what we call T. This is the linear mapping from V to W. Now I have vertical arrows. I can think of vertical arrows here. These are just mappings. I have a mapping from V to R4, right? Because V, remember, was the vector space of polynomials of degree no more than 3, right? That has a dimension of 4. Once I've fixed a basis, which is what I did, I called my basis B sub V. I obtain for free an isomorphism from V to R4. That's what we were talking about in the review, right? Now this correspondence is exactly the following. So you take a vector V, and it's mapped to, remember this symbol means is mapped to, that's defining this map. So V is mapped to the coordinate vector of V, but I'm looking, of course, with respect to the basis that I've fixed for V. So this is the coordinate map with respect to this basis B sub V. All right. Now I get the same thing for W. W, remember, was the space of polynomials of degree no more than 2. That is 3-dimensional. So I know I get an isomorphism to R3. And of course, this isomorphism depends on a choice of basis. Specifically, a generic vector, little w living in capital W, is mapped to its coordinate vector with respect to the basis that I chose, B sub W. And recall that B sub V and B sub W were just the standard bases for the domain and the codomain. All right. Okay. Now, a matrix A is called a matrix representation of T if the diagram commutes in the following sense. So I'm going to get a mapping. Whoops, let me switch colors here. I'm going to get a mapping from R4 to R3 given by multiplying on the left by A. Yeah. So in this notation, I mean A, after I multiply a vector on R4 on the left by A, I obtain a vector in R3. Yeah? Okay. So commutativity, so here's my diagram that I get. Now, commutativity of the diagram precisely says that you can take any route to get to whichever destination here. So, for example, let's start with a vector here living inside of the vector space V. What I'm going to do first is apply T, right? So, okay, so I'm starting off with a vector, little v, we'll call it, living in capital V. So I'm starting off with a little v, living in capital V. And I'm applying T, right? So this is this first leg of this path. So I started off with an element, little v, living over here in capital V. I applied T, right? Now what I'm going to do is go down this way, right? So the vertical arrow going down is the coordinate map where I look at my vector with respect to the basis for W. So I'm doing this. B sub W. There. So that is the purple path. All right. Now let's sort of draw another little color in here. We'll make a blue path or something. Okay. So I'm going to start now. Or wait, what I could do is extend this here. So make the diagram nice and perfect here. Okay. So I started off with my vector over here, living in V. So I'm going to start at that same vector. I called that vector V. And I'm doing this second path. So I'm going down here first, right? So I started off with my vector V, and I went vertically downward first. Instead of going to the right, instead of applying T, I'm going down and I'm applying the coordinate map. So I'm applying the coordinate map. So I'm looking at my coordinate vector with respect to my basis for V. All right. So that's the first leg of this path. The second leg is, of course, going horizontal this way. All right. That mapping, as I just explained, is multiplication on the left by A. So I just multiply this on the left by A. Right? Now, commutativity of the diagram says that these are equal. So when this happens, we say that A is a matrix representation of this linear map. And it is, of course, with respect to these bases, because, look, I have the bases showing up in this equality, in this equation. All right. Now, notationally, this matrix representation is denoted as follows. So let's see, let me write down here in a different color. No, I can do white here. So the notation for A is the following. Whoops. Okay. So the notation for A is the following. So it's a matrix representation of T. So in the notation, I will have a T. But it's a matrix representation, so I put brackets. And it's with respect to given bases for the domain and the codomain. So I put the basis for the codomain first, which the codomain was W and my basis was B sub W. Then I put a comma, and then I put my basis for my domain. My domain was V. My basis was B sub V. Okay. So altogether, what we have is the following. We have that a matrix representation is a matrix for which the following is true. Let's see here. So I'm just going to rewrite this equation that I have upstairs. So it's T applied to a vector V after looking with respect to my basis for the codomain. This is equal to some matrix, which we're calling the matrix representation, with respect to B sub W and B sub V. Whoops. B sub V. And then I multiply that by this coordinate vector for V with respect to the basis for V. Okay, so this is the equation that defines a matrix representation. And you see why the notation is why it is. Or you see why the notation is the way it is, I should say. right? The reason being is because it's good for bookkeeping. See, look what happens here. Like when I've written it in this form, the basis for V, the bases for V, those symbols sort of annihilate, right? Yeah, because they're sort of stuck together. And I'm left with TV and I'm left with the basis for W, and that's what I'm getting on the right. You could sort of think about it like that. All right, so I'm just going to erase these hash marks here. Okay. Now, so that this makes sense, let's sort of emphasize what dimension this matrix representation has to have here. So let's just make a note here that the matrix representation for T with respect to these fixed bases, right? Let's sort of think about it just from the diagram, right? So over here in the diagram, I called it the matrix A, but it's taking a vector in R4 and I'm multiplying on the left by some matrix to get a vector in R3, right? So I know I have to have a 3 by 4 matrix. So this matrix has to be a 3 by 4. 3 by 4. Okay. So that essentially defines what it means to be a matrix representation. Whoops, where's this? Yeah, let's go up here. All right. Now, how do I find it? All right. So this was this aside here, sort of defining what a matrix representation is. All right. So let me go ahead and put my little squiggle here. All right. So now let's actually go about finding this matrix representation. And it's actually not hard to find. We will prove that this is the correct thing to do at a later date. But what I'm going to do is the following. Okay. So the basis for V, remember, was a standard basis. It was 1, x, x squared, and x cubed. Right? Okay, and let me sort of, so that this is how we finding this matrix representation. BW, BV. Okay, so you write down your basis for your domain. Now what I'm going to do is I'm just going to apply the linear map to each basis element. All right, so I'm going to take T, I'm going to apply it to 1. Then I'm going to take T, I'm going to apply it to X. And then what I'm going to do is I'm going to take T and I'm going to apply it to X squared, so on and so forth. All right, so I'm going to take T applied to X squared. And then I'll take T and I'll apply it to X cubed. Okay. Now in working this out, it looks like T applied to 1. Let me see here. Let me look at I have the function written down here. Okay. Okay, so T applied to 1, it looks like is, so it's 1 plus x squared. 1 plus x squared. Nice. So T applied to 1 is just 1 plus x squared. All right. Now let's look to see what happens if I apply T to x. T applied to x, it looks like is just, oh, that's pretty easy. It's just x. Yeah. So it looks like T fixes x. All right. Now T applied to x squared, it looks like is, that's not too bad. It is, it's just 2x squared. Yeah, it's just 2x squared. 2x squared. T applied to x cubed is just 1. And that's it. Pretty straightforward. All right. Now the next step that I have to do is the following. It turns out that in order to construct the matrix representation, I just take these vectors and I look at the coordinate vectors. So, okay, so the matrix representation of T with respect to bases B sub W and B sub V, it turns out, is given by doing the following. Okay, so I take T and I apply it to 1. I take T and I apply it to X. I take T, I apply it to X squared. I take T, I apply it to X cubed. And then let me actually make a little bit more space here. Maybe, yeah, I need a little bit more space just so it's not so cluttered. So T applied to 1, T applied to X, and then I have T applied to X squared. And then lastly, I had T applied to X cubed. Okay. All right. Now, I want to construct a matrix. Now, these are going to, they're going to turn into columns of a matrix. But right now it doesn't make sense, right? Because t applied to 1, look, is a polynomial 1 plus x squared. It's not a column vector. I need to turn it into a column vector. The way I do that is I look at each of these vectors. Now, these are vectors in W now. I look at their coordinate vectors with respect to the basis that I chose for W, right? So I just come over here and I look at the coordinate vector with respect to W. Same thing for the second output. I look at the coordinate vector with respect to W. Here I look at the coordinate vector with respect to W. And then lastly, once again, I look at the coordinate vector with respect to W. Yeah. Okay. So let's go ahead and determine those coordinate vectors. All right. Now these are actually, pretty straightforward to determine. For example, t applied to 1, that was the polynomial 1 plus x squared. So its coordinate vector with respect to my basis for W, and let's go ahead and write down the basis for W here, just so we don't forget. This was still just the standard basis. This was 1x x squared. But of course, it's the standard basis for W. Okay, so I look at the coordinate vector of t applied to 1 with respect to this basis, right? And you can convince yourself that this is the vector 1, 0, 1, right? So I do the exact same thing for the 3 remaining output vectors, right? Okay, so it looks like first off, what I'm going to get is the vector 1, 0, 1. Okay. All right, t applied to x was x. So its coordinate vector with respect to the standard basis for P2R for W is 0, 1, 0. Okay. T applied to x squared was the polynomial 2x squared. So with respect to the standard basis, its coordinate vector is 0, 0, 2. Now the last vector, t applied to x cubed, was 1. With respect to the standard basis, this is just 1, 0, 0. 1. Oh, let's hold on 1 second here. Yeah, this was just 1, 0, 0. So we have a 1, whoops, 1, 0, 0. Okay. That's my matrix representation. All right. And it is, in fact, as we conjectured, a 3 by 4 matrix. So this is of size 3 by 4. Okay. Now, let's sort of check commutativity of the diagram, like with an explicit example. So let's suppose, for example, I had a vector. Oh, wait, okay, so let me write commutativity of the diagram, what it states. Okay, so commutativity of the diagram, what it says is the following. It says if I take t and I apply it to any vector, and I look at that output vector with respect to my basis for W, right? Because V is a vector in V, T of V is a vector in W, so I have to look with respect to my basis for W. Okay, this is supposed to be equal to the product of this matrix, which is what we're calling the matrix representation, yeah, with the coordinate vector of V, but with respect to the basis for V. Okay, so let's actually check to see that this holds. All right, so let's call this a check here with an example. Okay, so let's, for example, suppose that I don't know. Suppose the vector v living in capital V is given by something. Okay, so we just have to pick a generic element in P3R. Let's pick 1 minus x plus 3x cubed. Let's do that. Okay. So I want to check the right-hand side and the left-hand side of this equation. Okay, so let's do that. So the first thing that I'd like to do is probably take the coordinate vector of v. Okay. So the coordinate vector of v with respect to the basis for v, of course. Now this is simple to compute because I'm just taking the standard basis. The coordinate vector is So it's going to be 1, negative 1, 0, 3. Okay. Now, let's compute t applied to the vector v. This one is a little bit more annoying to compute, but we can still do it. All right? So remember, t applied to a plus bx plus cx squared plus dx cubed is a plus d plus bx plus a plus 2cx squared. All right. So let's try to see if we can compute this. So a is equal to 1, and d is equal to 3. A is 1 and d is 3 if the vector v is 1 minus x plus 3x squared. So a plus d is equal to 4. Yeah? And then plus bx. B is negative 1, so I just have a minus x. And then I have a plus 2cx squared. C is 0, right? C is 0, and a is 1. So I'm just adding x squared plus x squared. Okay. All right. Now in this equation, I need to take the coordinate vector of t of v with respect to w. So I have to look at the coordinate vector of t applied to v with respect to my basis for w, which is, of course, we call this b sub w, but it's just a standard basis. All right. Now again, this is no longer a vector in R4. It's going to be a vector in R3 because w is three-dimensional. So the coordinate vector is going to be 4, negative 1, 1. Right? I'm just looking at the coefficients here of this polynomial. Yeah, precisely because I'm taking b sub w to be the standard basis. All right, so yeah, let's check to see that this equation holds now. Right? Now here's my matrix. All right, so let me go ahead and write down the matrix now. Okay, so here's our actual check now. Okay, so this vector, 4, negative 1, 1, I'm conjecturing, so we don't know this is true yet. Let's put a little question mark here. I'm conjecturing that this is equal to the matrix representation multiplied by the vector v. The vector v was the vector, what was it again? It was 1, negative 1, 0, 3. 1, negative 1, 0, 3. So 1, negative 1, 0, 3. Okay, so that's what I'm trying to check here. All right, now let's go ahead and come back in here and write down the matrix representation. The thing that I'm conjecturing is the matrix representation. All right, so I can't quite remember what it is. I have to scroll back up here just a second. All right. All right, wait. I'm almost there. Aha, there it is. Okay, so let me write this down here so I don't have to keep scrolling because this whiteboard's really slow here today. So it's 1, 0, 0, 1. And then I have 0, 1, 0, 0. Wait, 0, 1. 0, 1, 0, 0. Yeah, 1, 0, 2, 0. Okay. So I'm just going to write that matrix down here. Okay. All right. All right. So the matrix representation, what we're conjecturing is the matrix representation is 1, 0, 0, 1. And then 0, 1, 0, 0. And then 1, 0, 2, 0. All right. Let's see what happens if we actually take the product of these matrices. Okay. All right. So I know that, so the dimensions looks like, it looks like the dimensions are going to work out because this is a 3 by 4. This is a 4 by 1. And, if I do my little trick here, I'm going to get a 3 by 1, which is what I have on the left. Okay, so the dimensions work out. So there's no issue there. Let's actually compute what we get here. Okay, so I'm going to get a 3 by 1. I know that for sure. Okay. Now, in the first entry, what I'm taking is the dot product, of course, of the top row of my matrix with 1, negative 1, 0, 3. So I'm taking 1 times 1 plus 0 times negative 1 plus 0 times 0 plus 1 times 3. You get 4. Right? And in the second entry, I get negative 1. And in the last, I get 1 plus 0, I get 1. Right? It works out. Yeah. So we do, in fact, have this equality. Yeah, our diagram commutes. This funky looking matrix here is the matrix representation of this linear map with respect to these fixed bases for the domain and the codomain. Okay. Yeah. Okay. So this is the end of the example now. All right. So we found an explicit matrix representation for a linear map. All right. So now what we have to do is just generalize this a little bit. Okay. So we're going to generalize this to a general situation, right? Where I don't necessarily know what the bases are. And okay, so this is like the generalization here. Okay. So this is how we generalize this situation. All right. So what I'm going to do is take a linear map here, right? Because it doesn't make sense to talk about the matrix representation of a linear map if you don't have a linear map. And it doesn't make sense to talk about linear maps if you don't have vector spaces. Okay. So what I'm going to do is the following. So let T be a linear map between vector spaces V and W. Be a linear map. My goal is to build or construct a matrix representation of this linear map. In order to do that, you must choose bases for the domain and the codomain. So what I'm going to do is let B sub V be a basis for the codomain. All right. Now I need to label these in some way. In the previous example, they were just 1, x squared, and x cubed. But here, I'll just call them V sub 1, V sub 2, etc., until I get to V sub n. Right? In particular, I'm assuming that V is n-dimensional here. Right? So let B sub V be a basis for this vector space V, for V. Okay? All right. Now, same thing goes. I want to let B sub W be a basis for W. Yeah, and it turns out I don't have to sort of write down the elements of B sub W, and you'll see why in just a second. Okay, so let B sub W be a basis for W. Okay. All right, here. Yes. Okay. So the matrix representation of T with respect to these choices of bases is the following. So it turns out that the matrix representation of T with respect to these choices, remember you put the domain, or I'm sorry, you put the codomain first and then you put the domain, right? It's quite easy to build. What you do is you build a matrix by specifying columns of the matrix, right? So what I'm going to do is I'm going to take T and I'm going to apply it to V sub 1. That's going to be my first column. My second column is going to be T applied to V sub n. And I keep going, etc. Whoops, sorry, not V sub n. V sub 2. V sub 2. All right, and then I keep going up on my ellipses until I get to my last column entry. It's going to be V sub n. Okay. Now, the only problem here is I was calling these columns, which I don't a priori know that they're columns because in the last example, they weren't even columns, right? Because when I applied T to X, I just got X, for example. Or when I applied T to 1, I believe I got 1 plus X squared. Those are not column vectors. What I have to do I have to force them to be column vectors. And the way I do that is I come over here and I look at their coordinate representations. I look at their coordinate vectors with respect to the basis that I chose for the codomain. Right? B sub W. And then I come over here and I look at the coordinate vector. I'm running out of space here. 1 second. Let me scooch this over here just a tad. Right. So I look at each of these vectors corresponding coordinate vectors with respect to the basis that I chose for the codomain. Right? Now this makes total sense because each of the V's, so V1, V2 up to Vn, those are living in capital V. If I apply T, those are living in W. So T of V1, T of V2, etc., those are all living in capital W. So I can take the coordinate map, or I can take their coordinate vectors with respect to the basis for W, right? So it turns out that this is the matrix representation of T with respect to these choices for my bases, right? And what it means is that this diagram commutes, right? So we have commutativity of the diagram. So we have my linear mapping from V to W. This is what we call T, right? But I have vertical arrows here, precisely given by what we talked about our review. These are isomorphisms to Rn, and we'll say Rm, for example. Rn to Rm, right? So here I'm assuming W is m-dimensional, right? But these mappings, of course, are coordinate mappings, where I just take a vector and I look at its coordinate vector with respect to whatever basis I chose. So here I'm taking a vector v. I'm looking at its coordinate vector with respect to the basis I chose. That was the basis b sub v. Likewise, over here, I'm taking a vector w, and I'm corresponding, to this vector w, it corresponds its coordinate vector with respect to the basis for w, right? And then over here, what I'm getting is multiplication on the left by this matrix representation, b sub w, b sub v. Okay. Now, I have commutativity of the diagram. Again, what that means is the following. Let's introduce some new colors here that we haven't used here. I'm tired of purple right now. We're going to use green. Yeah, we'll use green here. All right, so the green path, again, I'm starting with a vector v, living in capital V. Yeah? I apply t to v. That's the first leg of the path, so I'm applying t. Right? And then I look with respect to my what's it called? My basis. I look at the coordinate map, or I look at the coordinate vector, right? So immediately, the second leg is you look at the coordinate vector, right? Okay. Now, for my second color here, I don't know. We're gonna pick a different color here. We're gonna pick orange. All right. So again, I'm starting off at the same position. I'm starting off with V. The first leg is I'm looking at the coordinate vector of V with respect to this basis, right? And then I'm applying multiplication on the left by this matrix that we're calling the matrix representation. B sub. Well, I don't have enough space here. Yikes. So this is matrix representation. Wait. Yeah. Matrix representation of T with respect to these bases. Yeah. And then commutativity of the diagram just says that these are equal. Right. And this is nice notationally because you see like these inside of bases cancel, and I'm left with basis with respect to W and T applied to V, and then I'm getting a T applied to V over here, but in a slightly different sense. Yeah. So this is the whole sort of the idea behind a matrix representation. All right, so that finishes the definition here. That's the end of the definition. Okay. Now give me a quick second while I plug my laptop in before it dies on me. Alright, so we're going to look at one more... Yikes, we're going to look at one more example of this, and then we'll call it a day. Okay, yeah. Alright, so I'm going to clear this here really fast. And we'll look at one more example of a matrix representation where we won't take the standard basis anymore, right? We're not going to take the standard basis anymore, so it's gonna be a little bit more. I don't want to say convoluted, but just a tiny bit more involved than in our first example. Okay, so we'll do this example here. Okay, so this is our second example of the day, and it's only one tiny step in difficulty, or it's one tiny step of increase in difficulty than in our first example, let's say. Okay, so here's our example. Okay, so what I'm going to do here is I'm going to give you a linear map. Remember, we want to talk about the matrix representation of a linear map, so I need a linear map. And in particular, I need vector spaces. So I'm going to take V to be P2R, and I'm going to take W to be R2. Okay. And the linear map I'm going to give you, of course, is going to be a mapping from V to W. Okay, so it's going to be defined by setting t applied to an input. An input of V is going to be a generic polynomial of degree no more than 2. I know that has the form a plus bx plus cx squared. Okay, so that is going to be the output. So the output, of course, has to be a vector in R2 and W. The output I'm going to give you is, why don't I do A plus B and then A minus B over here. Yeah. Yeah, we won't make it too difficult here. So it's just A plus B, A minus B. All right. Actually, you know what? Why don't we include C here? I would like to include C. All right, so I lied. Let's do A plus B plus C, and then A minus B plus C. Okay, so I lied. There we go. So there's my mapping. A plus B plus C, A minus B plus C. Now, in general, you would want to argue that this is a linear map. It is a linear map. You just have to trust me on it. Okay, now the next step is to fix bases for my domain and my codomain. Fix bases for my domain and my codomain. Okay, so this is where the little the slight twist is coming in. Okay, I'm not going to choose the standard basis for V. Okay, remember in the previous examples, what we took, like in the first example, I should say, we've only done one example. I took the basis for my domain just to be the standard basis. I'm not going to do that this time. The basis I'm going to choose is the following. It's going to be 1, 1 minus x, and 1 minus x squared. Okay. Now, again, you'll have to trust me that this is a basis. If you don't believe me, you can go ahead and check it. Show that this spans V and that these vectors are linearly independent. Okay. So this is going to be my basis for my vector space V. Now for R, or for R2, for W, I will, just to make things, not terribly complicated, I will take, let's see here. I will go ahead and take the standard basis, right? So what's the standard basis for R2? Well, it's just the basis consisting of vectors 1, 0 and 0, 1. Okay. So there, I've chosen my bases for for V and for W. All right. So what do I have to do now? Okay, I have to build the matrix representation. Okay, so the matrix representation of this map with respect to these fixed bases that I've chosen. Remember, how do we define it? It's quite easy to define. What I do is I take T, I apply it to all elements of the basis for V, B sub V. So I apply it to 1, I apply it to 1 minus x, and then I apply it to 1 minus x squared. All right. Now, I have to, however, I have to look at these vectors with respect to whatever basis I chose for W. Now, luckily for me, I did choose in this case the standard basis, but we always have to look with respect to the standard basis. I'm sorry, with respect to the whatever basis I chose. Here, I chose B sub W. B sub W. B sub W. All right. Okay. So really what I'm doing here is looking at these corresponding output vectors here. So, okay. Okay. So T applied to 1. What is T applied to 1 here? Right? T applied to the polynomial 1, it looks like it's just the polynomial 1, 1. 1. I mean, not that it's the vector 1, 1. So I'm looking at the vector 1, 1. But remember, I have to look at this with respect to the standard basis. Okay. Now, T applied to 1 minus x is, let's see, it's going to be, so in this instance, C is 0, and A is 1, and B is negative 1. So it looks like I get 0, and then I get 2. So I get 0, 2, I believe. Yeah, 0, 2. 0, 2. So I have the vector 0, 2. But once again, you have to emphasize the fact that you have to look at this vector with respect to the standard basis. Okay. Now, t applied to 1 minus x squared. So in this instance, a is 1 and c is negative 1. Oh, look at that. I just get 0, 0. Wow, that's exciting. So t applied to 1 minus x squared is just 0, 0. All right, so I'm looking at the vector 0, 0. This is a vector in W, but I always, always, always have to look at the vector with respect to my basis. I have to look at a coordinate vector. Okay. All right, so now, because I'm looking at the standard basis, it's really easy to write down the coordinate vectors. In fact, nothing changes after I look at the coordinate vectors in this instance. Right, so what I'm getting here is 1, 1, 0, 2, and then 0, 0. Right? So that is my matrix. That's the matrix representation of my map. That's the matrix representation of my map. Okay, let's see here. Yeah. Yep, that looks good. Okay. So that's the matrix representation of my map. All right. So we'll put a nice little box around this here. Okay. Yeah, so this is what we denote matrix representation of T with respect to the fixed bases that I chose. Okay. Now, what you can do is ask yourself the following. So, how would this matrix representation T change? So let's ask ourselves a question here. Okay, so here's our question here. So what is this matrix representation? Whoops, and I goofed up over here. I need B sub W appearing first here. That was a mistake here. So I need B sub W and then B sub V. All right. So the question I do want to ask is, what is this matrix representation if instead, whoops. Yeah, instead of choosing the standard basis for the codomain, what if I chose something different? What if instead I took B sub W to be this basis here? 1, 1, and then 1, negative 1. Yeah? Okay, so we'll see an example of this, like, similar to this, I think, on... we'll do an example like this on Friday, where neither of the bases for the domain and the codomain are going to be the standard basis, so it'll be a little bit different. Yeah, so this is yet one step in difficulty from what we just did. But the sort of increase in difficulty is negligible, I'd say. Yeah. Okay, so the punchline here of matrix representations is, of course, the fact that any linear mapping from R3 to R4, for example, any linear mapping between Euclidean spaces is always, always, always given by multiplication by a matrix. Yeah. So the point of a matrix representation is to sort of think about any linear mapping, whether it's from Euclidean spaces or not, from any two vector spaces. The point of a matrix representation is to give you a way to think about it as the multiplication on the left by a matrix. Okay. All right. Yeah. So that's it here for today. We'll see you on Friday, hopefully. Let me clear this here real fast.